Okay. All right. So yeah, that's the title of my talk. Now it's complete. So yeah. So maybe I'll just say a couple of words about the motivation of this theory, this arithmetic set spaces, which was developed by Alex Bouillon, and it was in analogy to the differential algebra theory over function fields, where you fix a derivation to the base. So I'll just say a couple of words. I won't go too much into it. So for instance, so this is a little bit of differential algebra. So this is the let's say you fix your base field. Let's say for us, actually, you take the field of rational functions and take the algebraic closure, and you fix a derivation on this, actually. So some partial d, so it's a derivation. And as an example, you can just consider, let's say, there are many, you can maybe take this one, d over dt. And suppose you have x, say, a scheme over spec of R. Given this base data, this field with a derivation, and you have a scheme over that, then there is a functorial way to associate what are known as these jet spaces. So this is nth jet spaces. You can, that's again a scheme. And this was initially actually, I think this theory was initiated by Ritt, and then and Kolchin took it further. The idea was to actually study give an algebraic treatment to ODEs, actually, to ordinary differential equations, and see how their solution space behave. But then this found in many different applications over function fields. So I'll just say one, actually, one instance of these things. So this nth jet space, I won't say how you do it, but we'll see the analogous construction in the arithmetic setting. So in particular, let's take this particular instance when x is an elliptic curve. In particular, where is it? So let's say it's the elliptic curve given by this on the affine part. Then actually then if you look at the J2 of E, so all these jet spaces, they are fibrations, actually. So we will see in detail, actually, how they would behave in the arithmetic setting, and they're very analogous. So J2 of E, there is and if you look at the global sections of J2 of E, there is a non-trivial element, which is now known as the Manin map, actually. So this is theta. So obviously we know that O of E is just constants, but if you look at the J2 of E, then there is a special element, and in coordinates it would look like this, actually. So J2 of E, I'll write something, but so these jet spaces, these are these jet coordinates, actually. So x and y are the coordinates for E, and then you adjoin these new coordinates in a systematic fashion. So let's just assume that you adjoin the derivative coordinates of your space. That actually has there is a special function. This is known as the Manin map, actually. So this is this on an open chart, actually. This is not the global function, but no, okay. Derivative. Okay, so that's an expression, and it's a global section in J2 of E, but more so, one sees very easily that since this is a group scheme, J2 of E will also be a group scheme. What this is in fact, is a map of group schemes from J2 of E to GA, the additive group scheme. And as a consequence, actually, what happens is that, let's say if you want to evaluate on an R point, I mean, anything which has a derivation, that gives you a map as follows. This is a group scheme. And this obviously identifies with R. And then, given any R point of an elliptic curve, there is a systematic way which is known as the canonical lift to give a point in J2 of E. So as a consequence, and this is, again, would be at the level of R points. This map only exists at the level of R points, whereas this is a scheme map. As a consequence, this composition gives you a map from the R points of E to GA, and that's a group homomorphism. So this is the group homomorphism. And this is a special map. This map is known as, these are named after Manin. And Manin attributes it to Fuchs also. And as a consequence, you see that this guy has no torsion, actually. And so all the torsion points actually has to go to 0. So this Diophantine information is encoded, and I think it's the later torsion is actually the kernel. And this map, these Manin maps actually, this was used actually in the proof of, for instance, this Manin-Mumford for abelian varieties and by Manin and Bouillon, both, giving separate proofs. Okay, so that's kind of the motivation of these arithmetic jet spaces. So now the point is that Bouillon wanted to carry over these kind of geometry in the case of arithmetic. So what should really play the role of a derivation? So, okay, that's enough of differential algebra. So, okay, so then let me now So the remark is that, so the role of the derivation in arithmetic is played by p-derivation. And this is something that you have seen in the last week and in Jim's talk this week as well. And yeah, so what is a p-derivation? Let's just quickly recall. Most of you have seen it. So let's fix an R algebra. So let's fix R. And for us, let's say it's a DVR, and with no, let me first actually below, okay, right, the light. Okay, so let me first define quickly say what p-derivations are. Just remind you. So a p-derivation, we will just understand. I'll just write it this way. A p-derivation from A to B consists of this data that U from A to B is a ring homomorphism and it satisfies, and this delta is a set theoretic map from A to B such that delta of, say, AB Left-hand side, yes, thank you. Thank you. Okay, so these are the rules that we saw, which makes a p-derivation. And we also saw that this piece of data, this is equivalent to actually giving a ring homomorphism from A to the width vectors of B. So this is the length 2 width vector. PT will width vectors. So yeah, we fix a prime actually. Okay, so maybe I should say fix a prime. Yeah, and the correspondence is that if you have an element here, you simply take the first coordinate is u, and the second coordinate is delta of v, and that information is entirely encoded in this piece of information. So yeah, the moral is that for differential algebra, the structure of derivations is actually encoded in this algebra, in a ring of truncated polynomials, and in this arithmetic jet space theory, I mean, you're replacing these truncated polynomials with vectors. That's kind of the moral. Okay, so now I won't recall much about width vectors because we have seen that quite a bit. But let's quickly recall. Okay, and let's now fix a base. So to fix our R, this is going to be a dVr with a p derivation. Delta. So as an example, you just keep, it could be, so as an example, it could be ZP, or you take the ZP unramified completed. So they have a delta. And also we saw that associated with this delta, there is a ring homomorphism. So phi of A, which is given by u of A to the power p plus p times delta of A, is a ring homomorphism. Okay. Yeah, so the point of the talk then is that we'll now define these jet spaces, and then from there, in the case of abelian schemes over say R, we'll associate these filtered isocrystals, and in the case of NLP curves, we'll show that for the larger part of the moduli, I mean that these are crystalline actually. Okay, so let's first define this jet space actually. So let's define it at the level of functor points. So all right, so okay, so let's say X. So now we move to the category of p-formal schemes actually. So let's say X. With a small formal spectrum of R. In particular, we can just, for simplicity of these things, I mean, we can just take it to be affine. So this is affine. Okay. Now we define the nth jet functor. So this is we define. We define it to be so Jn of x at the level of b points. So this b is whatever separate completed p-adic rings actually. So that we define it to be this actually. So So it sees a B point, it makes a width vector out of that point, and then feeds it to X. So in the case when it's affine, I mean, let's just, yeah. So this is an R algebra map. So that's the key thing. I mean, let me just write. So this is in fact a map of R algebras. So this would be A to Wn of B. And let me just write the obvious thing so that it becomes even clearer. So so what does this mean? So this, as I said, we are looking at an element in here is a ring homomorphism like this. And A is an R algebra. And of course, one has to see how Wn of B becomes an R algebra. And that follows because since R has a p-derivation, follows from the universal property that we saw again last week, that this in fact has the analog of the exponential map from the universal property of width vectors actually. So then this, we can call it X delta. So this is the analog of the exponential map in the case of differential algebra. So you have that, and then since B is already an R algebra, you take the Wn of the structure map, and in this way, Wn of B becomes an R algebra. And then when we are looking at this set. Okay, so that's the nth functor, and we saw this probably a couple of times that in fact this thing is representable. So this Jn of x, this is the adjunction property and everything. So Jn of x is representable. So in Jim's talk you saw, and also I spoke about it once, but let's just again for completion see what it is. So if A has a presentation like this, it is as follows. So if A, let's say this is a bunch of variables, and you quotient it out by a bunch of polynomials. So let me say these are the bold. I'll make this bold to say there are a bunch of things. And then say p-adic completion of these things. Then Jn of A, then Jn of x is, in fact, it's representable. So it's represented by some ring, J sub n of A. So for the rings, we use a lower script. For the spaces, we use an upper script. So J sub n of A would be just, you take x and you adjoin these new variables up to n of them, and quotient out by the relation delta of f, delta n of f. And what are these things? Actually, instead of me explaining what it is, I'll just do a quick example, and it's the same example I did last week. So for instance, if x was say form a spectrum of say R x comma y, modded out by say xy, then J1 of x is the formal spectrum of J of R x comma y, and then you adjoin new variables x prime, y prime. That's up here, and quotient out by, this is the f, so this is xy, and then you apply delta of xy. It's going to be one of the generators of this one, and what is it? Well, you just apply the laws of derivation that we have. So you just get, so delta of xy will be x to the power p times delta of y. Now delta of y, I'll assign it to be y prime. So that will be y prime plus y to the power p, that's times delta of x, that will be x prime, plus p times x prime, y prime. So that would be my defining, one of the generators of the ID. Yeah, and that is J1 of x in this particular case. All right. Now these jet spaces actually, there are these maps actually, between them, which I referred to a few minutes back. All right, so from this, okay, one quick remark is that suppose our X is, in fact, a group scheme, then from this functor of points viewpoint, you can see that Jn of X will be a group scheme. You know, if, well, it sees a B point, I mean, if it needs to know how to add, well, it then becomes a Wn point of our original scheme, and the scheme knows how to add points. So it becomes a group scheme. So in particular, we've been interested in abelian scheme. So it's a remark. So, and yeah, so then so maps between these jet spaces. So there is this fundamental maps actually. So this one, which is the projection map. So this comes, so I have Jn of X, and it will map down to Jn minus 1 of X, which is known as a projection map. And how do you do it? Well, one way to see it, there are a couple of ways to see it. Through this algebra, we can see it, but from the functor of points viewpoint, let's say I have to specify for every R algebra B, which is whatever, separated, I have to specify another point in here. And then from the functor of points viewpoint, so that is precisely this set. Let's say A is affine. And this is exactly, well, I'm just copying it for the other one. So given an element in here, I need to specify an element here. How will we do it? Well, this is a map from A to, so if I have an element in here, then this is particularly a map from A to Wn of B. And then from Wn of B, you know that there is a restriction map down to Wn minus 1 of B. So hence you compose it. So given an element here, to specify this map, this is exactly you just go F and then compose with the restriction map in here. And that is known as a projection map. Generally, we denote it by U. And then another map is the Frobenius. That will again go from Jn of X, again a map from Jn of X to Jn minus 1 of X. And you can guess now that we'll use the Frobenius of the width vector. So then at the level of B points, again, if you want to specify it, well, this time now, instead of going by the restriction, from Wn of B to Wn minus 1 of B, we have the special map, which is the Frobenius, actually. And this Frobenius, you know, if I want to write down in this width coordinates, I mean, I would just write down the first one, which is given by x0 to p plus px1, and then the higher ones, were one can compute it, but as Jim says, nobody does it. Okay, so all right, so this is the Frobenius. So then this map is indeed an element in here. F simply goes to F composed the Frobenius. So these are scheme maps, actually. One remark I must say that the projection is in fact a map over SPIFR. However, the Frobenius is not. It's a map because the Frobenius moves the formal spectrum of far. So it's not a map over SPIFR, but what is true is that this is true actually, that this, if you call this is denoted as the Frobenius. So this has well, from the delta structure, there is the Frobenius, so that's the Frobenius. So it's a map like this. Okay. Now, what do we have actually? So we have a system. So from our scheme X, or formal scheme, we have created a system of schemes actually, Jn of X, which are known as the nth schemes. So if you just put them all together, so this is known as a prolongation sequence actually. So this is, maybe I'll put it as a remark. That, okay, so this is the base scheme, so that's, everything is over this. And, okay, I'll just write it this way now. So just for brevity, so. Okay, so we have this system, and point is that the system has a certain compatibility, that it is just not, I'm not stacking a thing like this with this. There's a certain compatibility, and the compatibility is that if you go by U and then phi, that is the same as you first went by phi and then U. And another thing, actually, I'll just say that we should really think that there's a delta structure. Actually, I've not introduced that, but it's very clear that the Frobenius is a result of a delta structure on the structure sheaves. But we don't need it right now. But maybe I should just say is that the phi from Jn of x to Jn minus 1 of x actually comes from a delta structure, from a delta map on the structure sheet. So maybe you have to push down or push forward O of Jn of x to So you have the structure sheet from Jn of x. You take the push forward, and then you lower star of the structure sheaf, and then you have a delta structure on these sheaves on Jn minus 1 of x. Okay. All right, so we have the system, and now we assume that, okay, now let A so let's say now let's take A to be an abelian scheme over SPFR. Then actually you can see that if I look at Jn of A, this is a group scheme, and you see that I can project down all the way to the base scheme actually. So in other words, I'll still denote it by U. I can project down to this, and as group schemes, you can. It's fairly easy to see that this actually is a surjection. So hence, as there is a kernel. And so NNs, and what are these NNs? So in particular, so this can be shown. So this is again a remark or a lemma, is that for n equals to 1, N1 is in fact it will be Ga to the power G, the formal group of formal additive group, where G is the dimension of A, the relative dimension of A over R. So given a scheme, or given an abelian scheme, actually you have these extensions of the abelian scheme by Ga to the power G. In particular, so maybe I'll make a small digression. Into these differential modular forms. In fact, so let's say in particular, say if you have A to be an elliptic curve, then this is in fact you get a sequence like this at the first level. Then let me just give you one example of these differential modular forms actually that come from here. It's fairly so one can define, and I will not explain more on this differential word. Actually, what that means, it's not a classical modular form, and in fact, it cannot be classical because the kind of information it encodes a classical modular form cannot. So you can define a differential modular form as follows. So if you define it at the level of test objects, what do? You have an elliptic curve A, and let's say you have an omega, which is a non-zero form on A. You need to specify a number actually. So at the level of test objects, so you define what is, so this was done by Bouillon, so you define this F1 as follows. Given an elliptic curve, I have an extension like this. So hence this is in this, and I call this as eta, as this extension of A by GA. Then this eta is in AGA hat, X of that, and that identifies with H1 of A. So you have a class in H1. And we have an element in H0 of A omega A. So what you do is that now, to produce a number, you use Serre duality to pair them. So this is Serre duality. And now, what's the feature of this modular form? I'm suppressing differential because it's not a modular form. It has an order 1, whatever that means. What is it actually? So okay, just note that F1 is 0. Well, omega is non-zero. So and this can only be 0 when actually eta is non-zero. And when can eta be 0 actually? So this is only when actually this extension is split. So note that eta is 0 if and only if extension is split. But then you can show from the universal property of these jet spaces that, which means that there is a map back from A to J1 of A, and which basically means that A has a lift of Frobenius on it. So extension split, which actually means that A has a canonical lift. By which we mean that there is a delta or a Frobenius on the structure sheaf of A. So in other words, actually this guy, F1, vanishes exactly at the points of canonical lifts. And these canonical lifts, and no classical modular form can be like that because, as you know, the canonical lifts on the moduli, they're dense. They're just Zariski dense. So, but this is a non-zero function actually. So that's why it's a differential modular form. And this one has a couple of applications actually in different geometry. Okay, so I wanted to make this digression to kind of show this F1. All right. All right, so let's get back to this. There's a weight, and the weight is minus, so it's -1 minus phi. So I have to explain what this phi is. So the weights are not integers, but the weight space is actually Z phi. This phi corresponds to the Frobenius actually. So the weight space is actually their delta characters of GM. So in the usual classical case, they are characters of GM. But then these, the delta characters of GM are basically, so weight space actually, this chi, any chi is actually a group scheme map from GM to GM. And one can show that this space of such chi's are actually these polynomials. In the classical case, you just had GM to GM, well, they're just phrasing things to the power in some integer powers, yeah.
Following the analogy with the classical situation, would there be a duality between N1 and J1 of the dual obedience scheme?
So can you say that again? N1 and?
Huh? J1 of the dual obedience scheme, because in the classical differential case, N1 would be the omega of a dual, and J1 would be the tangent bundle to a dual.
But yeah, it could be actually. But are you referring to the universal extension situation or no? The different.
So in the classical case,
the
analog would be a differential universal extension.
Yes.
If n is 1,
yeah.
N1 would be the
correct.
tangent space of the
correct. It will.
dual to the tangent space, but the tangent space is the analog of J1. So
yeah. Okay. Yeah, I thought a little bit, but didn't think it hard enough what you're saying. It might be true actually. Yeah. I mean, these things actually will come a little bit later in the talk also. Because as you can see that since this is the extension of A by GA, then there will be a map from the universal extension to this one. All right, so Okay, so maybe not this. All right, so, okay, so if I now, let me just copy this one half of the, that's the left half of the diagram. I'm not writing that. Now, we just saw that Jane of A, this forms a prolongation sequence. So in other words, I can drop by the projection U over there, or by the phi. Now, let's just remember the phi now. And so these are what are known as prolongation sequences. Precisely, if you just refine the definition with deltas instead of phis, these forms a prolongation sequence. And this is known as a canonical prolongation sequence. It's because it satisfies a universal property. I'm just adding names, but still, because he's a special guy. Okay, now, and then we have a system of these NNs actually. But the point is that it's very tempting. Okay, if you put an U here, then you can see very easily that, okay, this U should factor through NN. That's very easy to see actually. However, if you put a phi here, the Frobenius, you should not expect that there is a Frobenius in here. Because one reason is that if there is a Frobenius on these kernels actually, then the quotient of Jane of A by Nn is actually A. So that would mean that the Frobenius will descend to A. But that is a very hard thing to have. Generally don't have such things. So in other words, you cannot expect such a Frobenius on these NNs. But this is this is one of the theorems in this paper actually, is that, this is again, I'll write names, is that in fact there exists, so maybe I should write it here so that I can extend the, is that you can actually, there exist, okay, this guy, one second. It's a unique map of formal schemes from Nn for every n to n minus 1. Such that the point is this square has no hope of commutation actually. So this f is going to be there. This has no hope of commutation. But if you go compose one more time to Jn minus 2 of A, then it commutes. So maybe I'll name these maps. These are I, such that if you go by f, I, and then phi, that's the same as going by I and then going phi twice. So you go by I, and then phi square. That's the same as going by f composed I composed phi. So so these NNs become a prolongation sequence. It's not the canonical prolongation. It's actually it's a much simpler thing, and but there's a delay in the Frobenius, and we call it a delay. So so this is that. Okay, and well, the sketch of whatever proof. Well, it's why should such a thing be happen? This actually, morally, this happens because on Witt vectors, this is true that if you look at the Frobenius square, compose the Verschiebung, that is the same as Frobenius composed Verschiebung compose the Frobenius. And that is because, FV is P, multiplication by P in the width vectors, and that P commutes with F. So you can easily see that this is P times F, actually, both sides. So morally, this is why this thing is true. It's a, but of course, you have to prove something for this. Okay, so it's a reflection of that fact. All right, so yeah, one side remark that I wanted to say, but I have lost the opportunity, but I'll just still say it. I can't help myself. But you can actually check that the way we have defined jet spaces, in fact, if you take the Jn of Ga hat, that is in fact the width vectors as a scheme. Wn. It's isomorphic, the width vector. So the nth jet space is in fact the n plus 1th width vector as a ringed object. So I should have mentioned it long time back. Okay, let's come back to this. All right, so we have this now. So we are in the process of creating this filtered isocrystal. So let's see how we use this actually. So I'll just introduce another notation, and I'm sorry for introducing so late. So, okay, so I just introduced x sub n of a as characters of Jn of a to Ga hat. And you saw in the differential algebra case, we saw these Manin maps. They are actually elements. So there is an exactly analogous theory for these arithmetic jet spaces. There are Manin maps. And so this is not, what I'm saying is that this is non-trivial actually. So these are, it's not an empty space. So these are maps out from Jn of a to Ga hat. So then using this kind of relation actually, I'll write down I'll write down something and then I'll explain. So. Okay, now what is this actually? So these are characters out of Jn of a. These are characters out of nn plus 1 of a. And, well, let's just do it here. If suppose I have a map out from here, say a theta to Ga hat, what it's saying is that, or rather, in fact, maybe I should do it here. That suppose I have a map out from here to Ga hat, then I can pull it back via phi star, and then pull it back via I star to get a map out from nn minus 1. And this is this direction actually. Now, and this is just one level lower. Now I want to connect it with this one. Some mistake? N minus 1, thank you. Okay, yeah, okay. This is phi, this is f power star. One of them is a phi. Let's just write something and then correct it. Okay. Okay. So what this I'm saying is that okay. I mean, if you have a character out from here, then if you go up this way, if you go phi upper star, I upper star, and then f upper star, you get a character out from here. that is the same as if you go pull back this way. So what I'm saying is that this diagram is commutative, actually. It just follows from this pulling back via two paths. So this is commutative. And I have not said what HNA of A is. Well, this is just, I define it to be the quotient of this one with this one. That's the definition. And these are R modules. In fact, one can say that, see, actually, these are finite R modules. At every level n, these are finite, this one, and even this one. These are, in fact, free, in fact, R modules, a finite rank. So, but the rank increases for every n, as you can expect. So I define HNs to be this. So since we have this commutation, this induces a map F upper star from Hn minus 1 to Hn. And now we define, so now we define so this, it is easy to see, okay, remember that there are two maps actually, because these are prolongation sequences. There is these phi's, which are the Frobeniuses associated with the deltas, and then there are these, just the projection maps, which are morally kind of easy to handle. They're mostly harmless. So, now you can take the limit of these HNs with respect to those U upper star. You can pull back via the projection maps. So you can define, so we define this H of A as a direct limit of over the U upper stars of these HNs. Now, since at every level, Hn minus 1, and this you can see actually that this is in fact is a semilinear operator. So yeah, maybe I should say it here that in fact, remark is that F upper star is a semilinear operator. And that is simply because that the Frobenius is not R-linear. It moves the base by a Frobenius, by the Frobenius of the base. So yeah, semilinear means that F upper star of any lambda times x will be where lambda is in R, Frobenius of the lambda times F upper star of x, where lambda is in R. So as a consequence, you take the direct limit over U upper star, then at the limit, you have this semilinear operator on F upper star. Okay, now we will write down one of our theorems from this paper, maybe here. This is what I'm not writing Borg arrays again, but yeah. Okay, so I might not be able to explain much on but so okay, down here is the hot sequence, the first Debargha cohomology, and yeah, this is something that everyone must know. Up here, I have a bunch of undefined things actually. So H of A sub k is precisely this one tensored with the fraction field of k, fraction field of R. So maybe as a notation, so M sub k is M tensored R over k. Okay, and then there is a map from here, which we call it as upsilon, this one is the big phi, and this is an injection. Now I have to explain, yeah. Okay, but yeah, let me complete the statement where the dimension of H of A is less than 2 times the dimension of A. Okay, so one thing to note is that this is actually an increasing system. I mean, each Hn of A, I mean, these things are, the ranks are increasing, same with this one, but the point is that it stabilizes. I mean, this is a finite R module actually. And in fact, it's, yeah, as a vector space over K, its dimension is less than or equal to 2 times the dimension of A. And on this, it has a semilinear operator. What is X prime? These are kind of the primitive characters, actually. I mean, I won't be able to explain probably too much on this one, but I can kind of tell you how this map from H of A to H1 deram of A, how it's obtained, actually. This is obtained through the push outs of the extensions, actually. So 2 minutes plus 5, right? So. Okay, so yeah, so this filtered isocrystal, maybe I should remark, is exactly this one actually, this X prime of A. Yeah, so the filtration is, yeah, X prime of A is inside H of A, and you have the semilinear operator F, or F upper star. So that is, so this H of A sub K is the filtered isocrystal. And maybe I should, before I run out of time, showing you how actually these things are. Let me say the statement for the elliptic curve, and then I can probably say a few words more. This is I of A. This one embeds inside this one. Okay. Okay. I'll say a few words on this one. Just give me 2 minutes. Let me just state this theorem. So in the case of an elliptic curve, then actually this one can actually figure out the structure fairly easily. So if A So when A has a canonical lift, which means it has a delta, 5 minutes, right? Okay, so this is this thing, and the F upper star acts on these bases as gamma of psi 1, and I'll say probably a few words about the gamma, and otherwise, psi 2, and the smaller subspace is, in fact, is R some theta. Okay, this is in fact is a character out. So, but let me just that's not important right now. So this. But with respect to this basis, it acts as follows. So in both the cases, lambda and gamma are in R, but and the thing is that moreover, if gamma is not congruent to so this gamma, lambda and gamma is in R, and pi always divides gamma. Pi is always divisible by gamma. So now the question is that whether it's divisible by pi one more time, and if it's not, which is which depends on the parameter of the elliptic curve on the moduli space. This follows very immediately that this mod, if gamma is not 0 mod p square, pi square, sorry, p, then, oh, sorry. Drinfin model hang also. Yeah, so when gamma is not 0 mod p square, then h of a is weakly admissible, and which actually gives you what this Fontaine functor gives you this crystalline representation. Sorry? R of theta 2. Yeah, so theta 2, okay, so let me now say a few words about these objects. So theta, so what you have J2 of A. Out of that, we just mentioned that there is a non-trivial character out of J2 of A to GA hat. What is theta 2? How are these guys? They are actually, Hn of A is a quotient of home Nn plus 1 to GA modded out by these guys. So in other words, I could look at the image, I could pull it back on N2. So the composition will be, say this is the I. So composition is the image of theta in Hom N2 GA hat. And this is the image of theta 2 inside H of A, because H of A is a quotient of home Nn modded out by something. So that's it. And this psi 1 and psi 2, they are actually, well, they are representatives of some character out of N1 and N2. And these guys, so one more remark is that, so these lambdas and gammas, you should really think of them as modular functions actually. In fact, lambda is actually associated with that F1 that I wrote down a few minutes back. Because when you do this on a moduli space of, say, the elliptic curves, these would be modular functions. So gamma is a new modular function. So this lambda is actually, as I said, related to F1, and it was known to Bouillon. This gamma is another modular function actually. And it would be Hecke equivalent and, So it's the natural action of Hecke operators. It would be Hecke equivalent, and it would have a certain weight actually. I don't know exactly what the weight is. And I think I should probably stop now, or should not say more. I mean, just one. So this is weakly admissible. So by the Fontaine functor, you get a crystalline representation. Right, so the point is that, okay, one thing is that, see, this one, and we know that, that for the usual crystalline representation for, say, an elliptic curve is this guy, I mean, when you identify it with the crystalline convergence. Here, everything, this isocrystal, the filtrations are the same. In fact, these are even Hecke equivalent. If you do, let's take A to be a Jacobian of, say, a modular variety or something, it would even be Hecke equivalent. But the point is that this has this F upper star, and this has, from the crystalline, say, let's call it phi now. We don't think that, these are compatible. This semilinear operator is something not compatible with the crystalline structure. This is something that is right now unclear to us. And so in that way you get right now you can say that this is a priori looks like a new value representation, but one has to see. Yeah, maybe I should stop here.